Good morning. Today I will have a conversation with Dr. Debholkar. He's the director of the International Center for Theoretical Physics in Trieste, Italy, which was founded by Professor Abdus Salam way back in the 1960s. Dr. Debholkar is a theoretical physicist who works in the most difficult area of that field, which is quantum gravity. So that's combining quantum mechanics with general relativity, Einstein's theory of general relativity. And out of that comes something called quantum black holes. But we're going to talk about that later. Welcome, Atish.
Hi, good afternoon, Provez. It's a pleasure to be here and to speak to you.
Atish, when I read your second name, Debholkar, instantly to my mind came the name of Narendra Debholkar. He was a hero of mine. I never met him, but I'd heard of him. After all, you don't meet people on the other side of the border in Pakistan, So he's India, he is Pakistan. But before we go on to talk about black holes and everything else, tell me, why was he murdered? Who killed him? What did he stand for? How close were you to him?
Provez, actually, Dr. Narendra Debholkar, he was a very dear uncle of mine. Actually, when I grew up, we were quite close to him. Also, later on, I also felt intellectually quite close to him because he stood for the rationalist movement in India. He was a medical doctor by profession, and he was quite a remarkable person, actually, who somehow managed to combine intellectual rigor with public action. And they had a very important organization in the state of Maharashtra to eradicate superstitions, which might sound like something that is you might question why you need something like that, but it's very evident even if you are in a major scientific organization like Tata Institute of Fundamental Research, where I worked. Just 10 kilometers from that, there are all kinds of superstitions which actually prevail, and that organization stood for fighting against superstitions which are exploited by fraudulent godmen, irrespective of the religion. It had nothing against religion, but it was against exploitation of ignorance, and they had been fighting for a bill, actually, a law against superstition, and they had consulted various very eminent jurists, and who were convinced that India actually needs a legislation to address some of these very peculiar superstitious practices, which can be extremely harmful, especially to women. I mean, typically the people who are exploited by that are women or poor, farmers and so on. And somehow that was perceived by some of the misguided youth to be an attack against religion.
Was the killer ever caught? Do you know who it was?
Well, they are being, people have been caught, and the trial is several years have passed now, and certain organizations have been found to be connected to it, which are sort of very I would say very extreme, with extreme agenda, almost terrorist internal agenda. And but the trial goes on. I mean, I think I don't know when the actual justice will happen. And he was not alone, because after that there were 4 other assassinations of very eminent intellectuals and across India. So it was the beginning of a kind of you might say a conspiracy, actually, to attack. And the reason I actually got involved in it myself, I sort of left physics a little bit for a few months, and I really went to India to to demand that this legislation be passed. We managed to get signatures from some 3,000 scientists from India. Some 100,000 citizens signed onto it. And we actually successfully got this legislation passed. I mean, I played a small role in it. It's actually the colleagues who worked with him for 20 years who were responsible for getting this passed. But I got involved in it because I really felt that it was not so much because of my personal, of course I was very close to him, but more than that, it was really an attack on very fundamental constitutional principles of India, also on very fundamental beliefs underlying science. In fact, it was an attack on science itself, that you want to somehow legitimize pseudo-scientific thinking as being normal. And so therefore, I felt it was my responsibility both as a citizen and as a scientist to take part in it, and that's the reason I...
So it's quite incredible, isn't it, that we live in the age of space travel, and yet we are caught up in the superstitions of the age of caves of 1,000, 3,000 years ago. Why do you think we're having such difficulty? So that on the one hand, we're looking deep into the atom, we're moving out into space, and on the other hand, we are caught up in a mental freeze so that we can't move out and out of those disproven beliefs.
Well, one thing that I have learned from this movement is that it's necessary not to be sort of sarcastic or critical of this mindset from a very elitistic point of view, but what is required is some empathetic understanding, because oftentimes people have huge psychological or financial pressures in their lives, and they are looking for some simple solution to their life. And I mean, for example, I mean, as I said, in Tata Institute we discussed the Higgs boson and the quantum black holes, and just 10 years from there was a case of a person defrauding a couple as claiming to be the avatar of Lord Krishna. So Lord Krishna is an Indian god, but he was claiming to be the avatar of that Lord Krishna, and he defrauded them for several hundreds of thousands of rupees. He was coming in and going in front of the husband. He was sexually exploiting the wife and their teenage daughter, and all this was happening, and it cannot be tried under the Indian Criminal Code. So it requires a separate legislation, and it's clear that that family was under some pressures, and somebody fraudulent made use of them. So I think the criticism of this should be directed at the fraudulent usage of these kind of beliefs to enrich oneself rather than at the victims.
Okay, I won't even try to get into how bad things are on this side of the border here in Pakistan. Let's leave that for a later time. But let's now talk about good things.
No, but okay, before we go from there, I think, Provez, I also want to say that I have also heard from this side of I have been an admirer of your, you have been a voice of reason in a society which is similar to India, and the religions may be different or the superstitions may be different, but some of the challenges are similar, and so in that sense, we are all, comrades or connected.
Absolutely, no doubt about that. Well, look, there are a lot of people who are waiting to hear from you about black holes. Okay, but let me tell you, here's the paradox. There are two pillars of modern physics. One is Einstein's theory of general relativity, which includes the special theory. And the other pillar is quantum mechanics. Now, these strange things called black holes were actually the prediction of just Einstein's theory of general relativity. Out of that popped black holes. You didn't need quantum mechanics at all. So first, do you agree with it? And then, secondly, go on from there and tell us why you felt the need, or why do people feel the need to combine these two together? What's to be gained? Why is there such an urge on the part of theoretical physicists to do this?
Okay, so I think one must understand the general theory of relativity describes basically gravity at very large distances, all the way from black holes, stars, galaxies, all the way to the universe, the expansion of the universe. And this theory has been incredibly successful. I mean, even for example, to use your GPS, you in fact need corrections from the general relativity to be taken into account if you want to actually have very sharp predictions of where you are. So it works at very large distances, and quantum mechanics, on the other hand, has been tremendously successful at very short distances. Everything from atoms, nuclei, elementary particles, to all the way to your semiconductor technology in our mobile phone or this conversation that is happening. All that is really depends on quantum mechanics and our understanding of nature at very short distances. So even though these two paradigms have been tremendously successful, and it's actually amazing, sometimes physicists fail to convey how well we know what we know. I mean, we really know quantum mechanics and general theory of relativity so extremely well that we can actually predict what will happen 2 billion years ago. I mean, that was what the discovery of the black hole, the gravitational waves coming from black holes, which got the Nobel Prize for the LIGO experiment. These are waves that were emanated billion years ago, and we detected them today using actually an interferometer which uses quantum mechanics. So it's an amazing success of both general theory of relativity and quantum mechanics. However, when you try to bring these two theories together, there is a very serious contradiction. I mean, it's very serious, so I cannot explain, but roughly speaking, we know that the gravitational attraction between the sun and the earth is given by the Newton's inverse square law. This is something that we have studied in school, that the earth goes around the sun because of the gravity. And Newton's law of gravity actually follows from Einstein's theory of general relativity as a special, as a limit. But if you now put in quantum mechanics, what you find is that, in fact, the force between sun and earth, if you include the quantum corrections, which you expect to be small, instead of it being small, it's actually infinite. So this is something clearly something very unacceptable in a theory of in scientific theory, that you cannot have quantum mechanics applied in one domain and general relativity applied in another domain, but in the common domain there is a contradiction between them. So it's a bit like, I don't know, you cannot use general relativity on Mondays and Tuesdays and then quantum mechanics on Wednesdays and Thursdays. I mean, you want a coherent theory which describes all of nature. And part of the reason for this motivation is that actually in the history of science, it has always happened that when you try to resolve such fundamental contradictions, it always leads to a synthesis on a broader scale. I mean, one famous example is special theory of relativity, which was brought about trying to make sense of Maxwell's theory of light and electromagnetic waves and electric magnetism and Newton's mechanics, and those two things don't fit together. And if you try to resolve the contradiction between the two, you are naturally led to special theory of relativity. So therefore, it's a very powerful guide in our search for new principles and broader principles that cover all known phenomena.
Absolutely. We want to combine the two together, but the marriage doesn't work out. However, maybe you want to tell us a little bit about Hawking, why he felt that you simply had to bring them together, and that as a consequence of bringing them together, out comes something new, something that could possibly lead to an experimental observation, not now, but someday.
Yeah, so I think, therefore, if you want to bring these two theories together, you have to look at phenomena where both these effects are important. So if you look at a big black hole, which is, for example, in the middle of our galaxy, there is a huge black hole whose mass is equal to the mass of about 1 million suns. It's a massive. Nowadays, we believe that there are basically billions of black holes in the universe. It's something which was like a science fiction. Is now really, people are measuring things coming from a black hole. We are pretty sure that there are black holes. 2 Nobel Prizes have gone for the, but these are black holes where quantum mechanics plays very little role. But already this in the general theory of relativity, it's a really very spectacular consequence of general theory of relativity, that if a large mass, if the mass of the sun keeps on increasing, then what happens is that, you might remember, there is some escape velocity, that you need to throw the rocket up at a certain speed so that it escapes the gravitational field of the earth. if the earth became very massive, then the escape velocity will become equal to the speed of light, and then nothing can actually escape, even the light cannot escape, and that's the black hole. And this is such a bizarre consequence that actually Einstein himself didn't believe in it. In fact, he wrote a wrong paper trying to argue that black holes cannot exist in his theory, because he somehow looked upon black holes as a blemish on his otherwise perfect theory. So black holes, it took some 50 years for people to actually accept the notion that there can be something like this, where even light cannot escape from the gravitational field of this object. But then Hawking came along and he showed that actually, so therefore black holes are called black because they are really black, nothing can escape their gravitational field. But Hawking showed that because of quantum effects, black hole is actually not really black, but it is slowly emitting radiation, very much like a hot piece of metal. You know, the hot piece of metal is emitting heat waves and red light. Exactly in the same fashion, black hole is more like a thermal object, something which is hot. So black holes are not only cool, but they are also hot in terms of temperature. They have temperature, and it happens because we think there is nothing. When we think of our room, there is nothing, it's vacuum. But actually in quantum theory, there is always pairs of particles and antiparticles are being produced constantly around us, and they get annihilated. We don't notice them because that happens very fast. But near a black hole, if that happens, then it can happen that the antiparticle falls inside and the particle can escape to infinity. And the person sitting at infinity can observe that particle coming to her, and therefore the black hole looks as though it has temperature. And this discovery is very fundamental, and I can explain why.
But there's a very interesting thing that comes out of this. So, for example, if I take books in my collection over here, throw them into a black hole. Now, the black hole eats up everything, so the information would be lost, but that would violate quantum mechanics. So that led to Hawking saying that the two are not compatible. He said that at an earlier stage. Where does that issue stand today? In the age of superstrings, has that issue been completely resolved, or is there still some uncertainty about this?
Yeah, so I think there are two important questions to Hawking's discovery. The two questions arise actually, and I would say superstring theory has addressed the first question very satisfactorily, and I will describe what it is. It has to do with the entropy of a black hole, and which is what my work has been mostly in that direction. The second question about the loss of information and how black hole radiation is consistent with quantum mechanics, that question, in my opinion, still remains open, and I don't think there is a completely satisfactory explanation. There are strong indications that in string theory it should not happen, but I think that issue is far from being settled. But the reason we are optimistic is that actually even the first question is very important. The first question is the following, that if something has temperature, any body which has temperature, like let's say this gas in this room, you know, the room we had at room temperature, then there is something called entropy that you can define, which is a property of the gas in this room. And if something has energy and temperature, it should also have entropy. This is the first law of thermodynamics. So first law of thermodynamics tells you that when you heat this room, the entropy of this room goes up. Okay, so this is some concept that people defined when they were trying to devise steam engines, efficient steam engines. But it turned out to have a very fundamental physical consequence, because one of the very great physicists of the 19th century, Boltzmann, he understood that the entropy actually tells you the number of ways you can arrange the atoms in this room. So he explained the entropy of the gas in this room in terms of the arrangement of all the atoms in this room, and he was able to predict the entropy of the gas in this room. And that might look like a small thing, but it was in his time. The reality of atoms were also not established. You know, this is you are talking about 1860s or 1880s, that period. So you could actually, even though you could not see atoms, by studying the thermodynamic properties of the gas in this room, Boltzmann was able to establish that actually it must be composed of little atoms, you know, which are sort of bouncing around. And the number of ways they bounce around. If you take the logarithm of that number of ways, it gives you the entropy. Okay, so that was Boltzmann's very fundamental equation. So the question arises, black hole is really a hole in space and time. If the black hole has temperature and it has entropy, what are the atoms that are making up this quantum space-time, which can account for the entropy of the black hole? This was a question that was an immediate consequence of Hawking's discovery. And that question has been addressed very spectacularly in some cases for special classes of black holes in string theory in very detailed calculation. And that's as if we are able to look at the atomic structure of space-time. It's at the same level, I would say, it's in the same spirit at least, that in the way that Boltzmann was able to assert the reality of atoms by studying the entropy of the gas in this room, or the temperature, thermodynamic properties of the gas in this room. 21st century physicists can try to learn something about the quantum structure of space-time by studying the thermodynamic properties of black hole.
So are you going to tell us what those atoms of space-time are?
Yes. So we don't have, again, a complete understanding of those atoms, but a black hole in string theory actually is composed of some complicated objects which are like strings or membranes, and that in a certain regime of the theory, when the theory is weakly coupled, as the physicists say. So you basically, what you're able to do is that you're able to do the calculations in one regime and then sort of continue that answer to another regime where the black hole exists. And we completely understand in this regime where we are able to view the black hole as composed of lots of strings and branes, that the entropy can be fully explained by the way these strings are moving around, the membranes are oscillating. Because string theory has additional dimensions besides the 3 spatial dimensions and 1 time dimension that we have. So there can be little curled up small 6 dimensions or 7 dimensions on which there can be all kinds of complicated membranes and strings wrapped around, which for the person in 4 dimensions looks like a black hole. And the entropy of that black hole you can really understand exactly in terms of the motion of these membranes, very much like how you can understand the entropy of the gas in this room in terms of the motion of the atoms.
Yeah, okay, now we are getting into some really complicated stuff which one can't really understand without knowing something about string theory, the fact that one lives in a world of many dimensions, 11 dimensions maybe, and little bits of string moving there. But I saw one of your papers which calculated the entropy of a black hole and used the work of Ramanujan, Srinivasan Ramanujan. And that's quite remarkable. Ramanujan had nothing to do with physics. 100 years ago, the concept of black holes didn't exist. Nothing to do. Tell us about that.
Yes, that's a wonderful example of the unity of science. I think sometimes policymakers somehow think that, okay, we need technology, why do we need science? Or we need physics, why do we need mathematics? Or maybe we need some kind of mathematics, why do we need pure number theory? Ramanujan was a person who was kind of obsessed with just pure numbers. I mean, it has been said by one of his collaborators that it was as if each natural number was his personal friend. So he had this really extraordinary understanding of some beautiful structures and properties of numbers, prime numbers. And he did some rather amazing work in the 1920s. And he was like, some of you might have seen this movie of The Man Who Knew Infinity. It's a nice movie about Ramanujan's life. And he was interested in some simple questions like that. If I give you an integer, like say 3, how many ways can you partition it? You can write it as 1 plus 1 plus 1. That's one way to partition it. Or you can write it as 2 plus 1. So there are 2 ways to partition it. Number 5, you can partition it in some ways. It turns out that he had some very beautiful answer to this question of how many ways there are to partition an integer. And surprisingly, that question has a dramatic application in the physics of black holes. Is exactly when you're counting the entropy of black holes, you can reduce that problem to partitioning an integer. And then immediately you connect to a mathematics of Ramanujan that was done 100 years ago. So this is, this was actually quite astonishing, because in fact I came to Ramanujan's some recent work which is called Mach theta functions, purely by accident. I was working on some problem and I asked a number theorist, how do you do this particular thing? And he said, oh, no, this goes back to Ramanujan. This is a very important, difficult problem in number theory. And we ended up collaborating, and we wrote a very nice paper on, combining number theory with quantum black holes.
That's incredible. How number theory, which seems to have, it's one of the most esoteric branches of mathematics, how that should tie up with physics. That to me is such a beautiful example of the unity of physics and math. Do you have any understanding of why math works so beautifully in physics? There was the famous question that Wigner had raised. He said, he says it's very difficult to understand why these creations of our mind, mathematical creations, should find some kind of role in explaining physical reality. Do you have any insight into that?
No, I really think it still remains a mystery, that this, what Wigner called the unreasonable effectiveness of mathematics. I think a partial understanding of that is perhaps that human beings have sort of evolved. Some of it has to do with evolution, that we have this amazing ability to abstract general principles. See, for example, when you draw a triangle, a child, nobody actually has seen a perfect triangle, not you, not me. But if you draw a wiggly triangle, even a child sort of recognizes that there is a triangle. And then, so we have been able to abstract, this is sort of a little bit Platonic, this some universal notion of a triangle from, it's a kind of a model of actual triangle. And then we have been able to prove all kinds of amazing results about in Euclidean geometry, thinking about these abstracted triangles. So I think part of it has to do with our unique ability to do these abstractions. Another partial explanation, I think, can be found in what is known as the renormalization. Okay, I'm speculating here a bit, and let me just, it's a bit philosophical comment. But in physics, there is something called the renormalization group, which tells you that at low energies, even though in the fundamental equations, many infinite number of terms are important, at low energies, only a very small number of terms are important in the fundamental equations. So that's part of the reason why physics has been so powerful, or mathematics has been so powerful, is that if we really had to keep track of all the infinite terms in the fundamental equations, then we wouldn't be able to say anything meaningful. Okay, so that maybe partially explains it. But I think the mystery remains that, you look at the Dirac equation or the imaginary numbers, why do they play such a fundamental role in quantum mechanics? Or why does Einstein's equation describe a real black hole in such perfection, with such beautiful exactitude? This, or why does the Dirac equation describe the hydrogen atom so perfectly? I think it's, I would say there is an element of mystery there.
So then this brings us to the question of whether these mathematical objects actually have an existence of their own, or whether we've imagined them up. So take something like imaginary numbers. A number multiplied by itself gives you -1. This seems to be just a creation of the brain, of the human brain. And yet, without that, you wouldn't be able to have quantum mechanics, the Schrödinger equation. And so the question is, I want your take on this. Do you think the imaginary number really exists, or is it a product of our particular brains?
Yeah, I mean, this is a sort of an, what would you say, extreme Platonic view, that he really thought that these universal exist independently of, they have their own reality. And I think there is some truth to that. I mean, I think I don't have a very principled view on this, but it is actually quite astonishing that imaginary numbers which were invented to solve algebraic equations, like you want to find a solution of x square is equal to -1. It has no solution in real numbers. But you say that it is either plus or minus this imaginary number. Okay, all this is fine, and then you get some very nice results in algebra. But why is it that amplitude for some physical process is a complex number, which is a very fundamental fact in quantum mechanics, that in quantum mechanics you calculate probabilities, but actually before you calculate probabilities of something happening, you first calculate the probability amplitudes, and then you take the absolute value square of that. And those probability amplitudes are not real numbers that we are used to, for counting. They are necessarily complex numbers. And lot of the things like all this quantum interference depends very crucially on the fact that we are dealing with complex numbers and not real numbers. So why nature has this complex number so deeply embedded at such a fundamental level is really I don't know the answer to that question.
Yeah, you simply could not have quantum mechanics. You couldn't have mobile phones, as you said earlier, without having complex numbers. And so it's incredible. It's such a mystery, still remains a mystery. But we were talking of Ramanujan earlier. The institute that you head, the International Center for Theoretical Physics, founded by Abdus Salam. Salam actually solved the problem of Ramanujan when he was in Government College, Lahore. And Ramanujan preceded him by, I think, like 20 years maybe. Yeah. So here you have on the subcontinent Ramanujan and Salam. They never met, yet their brains were trained in very similar ways. So there's something very universal about us human beings, our abilities to understand the world, to create mathematics. And I think that's one of the things that ICTP is bringing out as part of its mission.
Yes. I think Salam has this very nice quote that science is a common heritage of and creation of all humankind. And both these things are important. It's a common creation and common heritage of all humankind. Of course, he said mankind, but okay, now we should add humankind.
Humankind now. That's the politically correct way of saying it.
Yes, because, but it's clear that if you look at, there are wonderful discoveries in the Indian tradition, in the Arabic tradition, in the Chinese tradition. And there is, it's important to understand and appreciate this unity of the scientific thought. And ICTP actually wants to play that role in the modern times, that we really bring together scientists from all over the world. It's a kind of a hub, meeting point where East, West and North, South meet together. We have some 5,000 scientists, 6,000 scientists every year coming from all corners of the world, from Nobel laureates to beginning graduate students. And this is the wonderful place. It's like a Makkah of physics, and that's why I'm very proud of, and I also feel, that was one of the reasons I sort of agreed to take upon this role, because this very special mission of ICTP to bring the world together through science and to bring science, make scientific resources available to the entire world in overcoming all the barriers of geography and gender and economics and ethnicity. This is a very, very, very important mission actually, especially in today's climate, to assert the great importance of science. I think science has somehow lost a little bit of its luster in the recent times, I feel, partially because of fake news, or perhaps scientists themselves are a bit responsible for maybe overselling themselves. I don't know what is the reason. Also, there have been attacks from fashionable philosophical traditions like postmodernism, I think, which I don't really subscribe to. But the end result is that it has somehow brought down some of the fundamental Enlightenment values that underlie science. And I really think, this international character of science is actually tells you the universality of these ideas. So if you look all around the world, you'll find major advances happening in very different civilizations at different times. And So I think we want to make such opportunities. I mean, we basically, the ICTP would like to see that Ramanujan was almost lost. You see, Ramanujan was managed to succeed because he got in touch with Hardy. And I'm sure there are many such Ramanujans in Africa right now or in India who do not get the opportunity to express their creativity.
And to stop you here, Salam would have been lost had he not gone to Cambridge, had he not worked over there in the most challenging theoretical physics environment of his time. He wouldn't have ever got a Nobel Prize had he not gone to Cambridge.
Yes, yes, exactly. So I think that's very important to make these opportunities available to everybody. And as you said, these examples of different ideas, coming from different corners of the world, same ideas coming from different corners of the world, sort of assures you that, science is indeed universal, and it really doesn't matter whether what is your religion, where you come from, those ideas somehow stand on their own.
Yeah, I totally agree with you. For me, Salam is as much from here as Chandrasekhar is, or as Hargobind Khorana was. These are all people who have come up from this soil, and we in Pakistan should consider them as our very own. They belong to this soil. They are our people. They are our heroes, our scientists. And so we should be prepared to acknowledge everyone from Ibn al-Haytham through al-Biruni, through Aryabhata, through Bhaskara, through all of these people. This is really the universal heritage of humankind.
So in fact, I might want to tell you that ICTP in fact has started a new initiative actually after I became the director. We started international chairs to bring in distinguished scientists. The first one is actually going to be named after Srinivas Ramanujan, and it will be occupied by quite an eminent number theorist, a collaborator of mine, Don Zagier. But part of the idea is, of course, to bring all these scientists and mathematicians to ICTP, but other part is to celebrate the non-European contributions of science. So the next one we are thinking of is to name after Al-Hasan ibn al-Haytham, who was credited to be the founder of the scientific method, one of the...
Yeah, he's the one I just named, except that in Urdu you say Ibn al-Haytham, but it's the same person. It's
the same person.
Haytham in English, in Urdu it's Haytham.
It's Haytham, okay.
Yeah, it's in Arabic it might sound different, I don't know, but
so he made extraordinary contributions to the science. I mean, the experimental method, in the 11th century, he made important contribution to optics. Roger Bacon is normally attributed with the scientific method, but actually Ibn al-Haytham should be really the person who is credited with it. So I think there are plenty of such examples, and I mean, of course, the idea is not to hark back on the past and sort of glorify our ancestors. We really want to use history to look into the future and not use history as a pedestal. But I think there is some serious scholarship is needed actually, because there is no doubt that there was a certain Euro-chauvinism and there was a colonial writing of history in the 19th century. Even if you read quite serious philosophers, you find them, writing what to modern mind looks like almost a racist, kind of superior sense of superiority of the European traditions. Oftentimes expropriating, like Greek, the miracle Greek, many people talk about as though it's the spring of all human knowledge, and it is European. But if you look at the Greeks of the time, they had more in common with Egypt and Persia and not with cowherds in northern Germany or in Britain. So, just the Greek science as being the fountainhead of European science is in itself a kind of appropriation of history. We should really look at the Greek science in the context of their time. when Euclid was living in Alexandria, which is in Egypt. In the context of his time, they were more oriented towards Persia, and try to understand, have a meaningful rewriting of history. Actually, a good friend of mine, Manjul Bhargava, he is a Fields medalist at Princeton, and he gave some number of very wonderful examples. Like Hemachandra had discovered the Fibonacci numbers several decades before Fibonacci, for some very interesting problems having to do with how many rhythms you can compose or how many meters you can compose. Or Pythagoras' theorem had proofs in the Chinese mathematical tradition, in the Indian mathematical tradition, several centuries before Pythagoras. So it's clear that mathematical and scientific abilities are distributed all over the world equally, and our task would be to make opportunities available so that those talents are harnessed for the betterment of society.
Absolutely. So it's China, it's India, it's Babylon, it's ancient Egypt. Science comes not just from Greece, but from there as well. Muslims are the last link between that ancient science and modern science, that of Galileo and Newton and so forth. So it's been wonderful speaking to you, but there's just one thing that I want to ask you about. There have been these fantastic papers, a couple of them recently, on traversable wormholes. I haven't tried to understand them in any detail. Have you?
No, so I think recently, as I told you, when people try to combine general theory of relativity and quantum mechanics, a very beautiful and very deep principle has emerged, which is called the holographic principle. And it's a very fascinating principle, and what that tells you, and now this has been established, many people, really hundreds of very detailed calculations have been performed to really, in some contexts. And what it shows is that a theory without gravity, you see, we think of gravity as a theory where things fall, in gravity things fall. But it turns out that at the quantum level, a theory of gravity is exactly equivalent to theory without gravity, where things don't fall. In fact, a theory very similar to the one that describes how the nuclear forces work. It is known as quantum gauge theories. So a quantum theory of gravity turns out to be exactly equivalent to quantum gauge theories, or a theory of the nuclear force, roughly speaking, in one lower dimension. And that's why it is called a holography, because it's like a hologram. The gravity, that one less dimension is the hologram of the theory of gravity. And it's almost an incredible, unbelievable principle. And in fact, it's not even sufficiently appreciated, I would say, even among my physics colleagues, that it's a very dramatic advance in our knowledge of both gravity and quantum gauge theories. And it's going to keep us occupied for several decades. I don't think we have fully understood the implications of this theory. And one of the consequences of this is that there is a notion of quantum entanglement, which is now used for quantum computing, for example. That, and this was what Einstein called the spooky correlations, that you can have a photon here and a photon in Andromeda galaxy exactly correlated with each other. It's called quantum entanglement. So if the photon that I see, a particle, is spinning upwards, the photon over there will always be spinning downwards. And if I find the photon to be spinning in this way, the photon there will be spinning that way. So if I perform a measurement here and my friend performs a measurement over there, we will always find correlation of this kind, that they are exactly anti-correlated. Now this apparently, the wormholes that people have encountered show that this entanglement has some very close connection with the geometry of space-time and having smooth geometry. And one of the solutions is the famous Einstein-Rosen-Podolsky wormhole solution. So somehow exact entanglement in quantum theory of this holographic theory is related to a smooth geometry with wormhole-like geometry. So I think these explorations are, I would say they are still in a very preliminary stage. I wouldn't want to
Okay,
jump
but you
too
know,
far
the
ahead.
claim was so wonderful that you can traverse a galaxy in this much time by jumping into a wormhole, and that you could survive it. And I think this is a calculation done by Maldacena and forget the other name. And that the accelerations will be such that humans could survive it. Of course, they don't tell you how to build those wormholes, how to get those black holes close enough or whatever, how to create that geometry of space-time. They don't tell you that. They probably can't tell you that. Anyway, we've pretty much reached the end of our time. So, Atish, it's been really a delight speaking with you. And I do hope to be able to see you in physical person sometime, somewhere.
Thanks, Purvez. I also look forward to seeing you maybe at ICTP, or if not in Pakistan.
Oh, you'd be most welcome over here.
Okay. Thank you.